In section 7.2, we move on and we are going to be talking about the central limit theorem as it applies to sample proportions. So this will be different than in section 6.2 when we were talking about individual values and their probabilities uh, their probabilities. It was also different than 7.1 when we were talking about sample means and their probabilities. Now we're going to be moving on to sample proportions. Suppose that a random sample of size n is obtained from a population in which each individual either does or does not have a certain characteristic. The sample proportion, denoted p with that little symbol over the top, and the way we read that is p hat, is given by p hat equals x over n, where x is the number of individuals in the sample with the specified characteristic. Also, just a reminder that n is the total number of items in the sample. The sample proportion p hat is a statistic because it's from a sample that estimates the population proportion, which we call p. So that statistic is a point estimate of the population parameter. Example 7.4, in a Quinnipiac University poll conducted in May of 2008, 1,745 registered voters nationwide were asked whether they approved of the way George W. Bush is handling the economy. Of the 1,745 registered voters, 349 responded yes. Obtain a point estimate for the proportion of registered voters who approve of the way George W. Bush is handling the economy. So what we're looking for is those who approve of the way he's handling the economy. So our p hat would be the number that approve. 349 said that they approve of the way he's handling the economy out of the total sample size, which was the 1,745. And then we will go ahead and grab our calculators and that's a division problem, 349 divided by 1,745. And that gives us exactly 0.2. So that is our point estimate, saying that approximately 20% of people from the population from our sample, that's what we would say is about 20% of people from the population are approving of the way that he's handling the economy. The shape of a sampling distribution. As the size of the sample n increases, the shape of the sampling distribution for the sample proportions becomes approximately normal. And again, that's going to be very important for us. We've got all sorts of information and characteristics of things that are normal shaped. And so this is, as we get a large sample size, our distribution becomes approximately normal. The center, the mean of the sampling distribution of the sample proportion equals the population proportion. So in other words, if we take a whole bunch of different samples, and then we find the mean of those different samples, the mean of that should theoretically is going to be equal to the population proportion p. The spread of the data, the standard deviation of the sampling distribution of the sample proportions decreases as the sample size n increases. So again, just like we saw with sample means, the larger our sample size, the smaller our standard deviation will end up being. Example 7.5. According to a time poll conducted in June of 2008, 42% of registered voters believe that same-sex couples should be allowed to marry. Describe the sampling distribution of the sample proportion for sample sizes n equals 10, n equals 50, and n equals 100. So the key thing here is, like we just said in our last slide, when n is 50, we have a certain standard deviation, and then it doesn't really matter what it is. But as that n value grows to 50 and then finally to 100, that standard deviation is going to decrease. So when n is 10, the standard deviation is larger In other words, the data is more spread out, is larger than when n increases to 50 or 100. 100 would have the smallest standard deviation because it's the largest n value. 10 would have the largest standard deviation because it's the smallest n value. So that's what this question is talking about. For a simple random sample of size n with a population proportion of p, the shape of the sample, number one, the shape of the sampling distribution of p hat is approximately normal, provided that n times p times 1 minus p is greater than or equal to 10. So remember what that means. Your sample size times the proportion of individuals in your population that have a certain characteristic. And then if you remember 1 minus p, that's the complement. So that's the proportion of individuals in your population that does not have the characteristic that you're talking about. And so if you are multiplying those three things together and you get a number greater than or equal to 10, we would say that that sampling distribution for p hat is approximately normal. Number two, the mean of the sampling distribution of p hat is mu sub p hat equals p. We already mentioned that the mean of the samples should be equal to p. Number three, the standard deviation of the sampling distribution of p hat, which is sigma sub p hat, and that's going to equal the square root of p times 1 minus p divided by n. So the proportion of people, of individuals in the population that have the characteristic times the proportion that do not have the characteristic. So have it, do not have it, and then divided by the total number of items in your sample, and then you take the square root of that whole thing. I'll show you how to do that on the calculator. It's not terribly complicated, but you do want to make sure that you're typing that correctly into your calculator. We do want to recall that when n times p times 1 minus p is less than 10, then we would go back and we would use our binomial distribution to calculate the probability, because then your sample size is just not large enough to be able to turn this thing into a normal distribution. It would still be a binomial distribution. We require that the sampled values are independent. Otherwise, we can't use this process. Because remember, if they are dependent, that means the outcome of one will affect the outcome of another. And so we do not want that to happen. So we want to pick a large quantity of values, or be able to choose from a large quantity of values. So when we're sampling from finite populations, this assumption is verified by checking that the sample size n is no more than 5% of the population size, uppercase n. So in symbols, that means lowercase n is less than or equal to 0.05 times uppercase n. But regardless of whether n times p times 1 minus p is greater than or equal to 10 or not, the mean of the sampling distribution is still, or of p hat, is still going to be p, and the standard deviation will still be that expression we talked about in the last slide. Example 7.7. According to the Centers for Disease Control and Prevention, 18.8% of school-age children aged 6 to 11 years old were overweight in 2004. In a random sample of 90 school-age children aged 6 to 11, what is the probability that at least 19% are overweight? So let's start out with identifying the different parts that we have here. Notice they did a survey and they found out the population proportion for overweight children was 18.8%. So that is P. Well, I shouldn't say P is equal to 0.188 because we have to write it as a decimal. When we go to the problem, we're just going to be able to figure this out now. So we know that, here's the other one. N is 90. All right, and then this is going to be what we're looking at for our probability. So we're trying to find the probability that p hat is at least 19%. So greater than or equal to, we don't need the or equal to, but 0.19. Now, in order to do this, just like we did our other problems in section 6.2 and 7.1, we are going to need to find the mean. And our mean in this case is the population proportion. And we also need to find the standard deviation. So that's where our formula comes in. Sigma sub p hat is equal to the square root of p, which is our 0.188, times 1 minus p, so I'm just going to put 1 minus 0.188, divided by n, which we said is 90. I'm inserting this in because one thing I realized that I forgot to talk about was the whole idea of, is our sample size large enough? So what we should have checked right away here is to make sure that n times p times 1 minus p is greater than or equal to 10. So let's check that out for this problem. We have a sample size n of 90. We have a p-value of 0.188, and then 1 minus 0.188 is our 1 minus p-value. So let's check that out here. Clear this off. So 90 times 0.188 times parentheses 1 minus 0.188. And in this case, we get 13.73. So that does assure us that our sample size is large enough to be able to assume that this is a basically normal, approximately normal distribution. So that is one thing that I think I forgot to mention in class, but I want to make sure I point that out in the video, that we should check that first before we even go ahead and start using that normal CDF. So to do this problem, we're going to type in the square root of, so second and x squared. Then we're going to type in 0.188, and then parentheses 1 minus 0.188. Close our parentheses, and then divided by 90. And so our standard deviation is 0.0412. We'll keep 4 decimal places there. So standard deviation of p hat is 0.0412 if we round that off. So those are the two values we need. If we're looking at our picture, remember what that means. We kind of think about this. And since I don't have much space at the bottom, I'll just write it here at the top. But our mean is the 0.188. And then if we add that standard deviation, so 0.188 plus 0.0412, we're going to get 2. I'm just going to go 3 decimal places here. So 2.29, no, 0.229. And then if we add again, plus 0.0412, we're going to get 0.270. And we can keep going that way. We also want to go the other direction. So if we take that 0.188 and subtract 0.0412, we're going to get 0.147 if we round that off. And again, we can label that, but here's the key. We're looking for 0.19, which is right here, right next to that 18.8, and we're looking for greater than or equal to. So just by examining our graph, knowing that the mean divides it into 50% below and 50% above, we would expect this number to be pretty close to 0.5, but a little bit less than that because there's not quite as many people above 0.19 as there is above 0.188. So let's go ahead and type this in. We do our second variables again, down to normal CDF, and our lower boundary this time is, when we're looking at that picture, since we wanted greater than or equal to the 0.19, our lower boundary is the 0.19. And then we want everything above that, so we're going to put in 1 second comma for the E99. Our mean value is 0.188, and our standard deviation 0.0412. And we'll paste that in and hit enter, and we get the probability, and my probability disappeared here when I shrunk the screen, but the probability that p hat is greater than 0.19 is approximately 0.4806. So like we mentioned, it's pretty close to 0.5, but just a little bit less than that. So 0.4806 would be our probability that 19% of the school-age children are overweight in that sample. For part B, suppose a random sample of 90 school-age children ages 6 to 11 years results in 24 overweight children. What might we conclude? So that means we're able to figure out p hat right away because 24 children fit into that overweight group as out of the 90. And we would just take 24 divided by 90 and we will get 0.266. That is our proportion. So, and I'm going to go, we've been going tenths, so 0.267. Now, just from looking at our graph, we can see that 0.267 is going to be way up here somewhere. Okay, so let's find out the probability and get an actual number here for a probability of somebody of our population giving us at least 24 overweight children. So we're going to go back, and unfortunately, I erased my values there, but we should be able to hopefully remember them. So second, variables, normal CDF, and our lower boundary this time is 0.267. Our upper boundary is still everything. We're not having an upper boundary. Oh, and it saved it. Okay, so our mean is still 0.188, and then the standard deviation is 0.0412. So we paste that in, and so what we're looking at is what are the chances that we have a sample that has that many students that are overweight in it. And when we hit enter, we find out, oh, that the chances of p hat being greater than or equal to 0.267 is actually very small. It's 0.0276, which is under 3%. So what might we conclude? Well, two options of what we can conclude here. One option is our sample just does not represent the population very well, and so we might have to do more testing, more sampling. The other option is to say that, you know, this data is from 2004. We're now many years after that, and so maybe the data has changed. So one of those two things, either our sample doesn't represent the data as a whole, or the data has changed over the years. So those are the two things that we might be able to conclude from that result. And that's the end of section 7.2. Again, just to emphasize what we've got going on here, in section 6.2, we were applying the normal CDF to individual values. Okay, and we were applying them, and we would plug it into our calculator. We'd find the mean, we'd find the standard deviation, and we would plug it in and find those proportions or probabilities. When we moved on to 7.1, then we were applying that normal CDF again, but this time we were applying them to sample means. Now, that didn't change the mean. The mean of the sample means was the same as the mean of the population, but it did affect the standard deviation. So the standard deviation, sigma, shrunk, we'll just say it that way, when you were dealing with sample means, because everything was drawn towards the center, and so that shrinks your standard deviation. In 7.2, in this lesson, we were still applying normal CDF, but this time we're applying it to sample proportions. Okay, and again, the mean, when we talk about the mean of p hat was equal to p, and then the standard deviation of p hat, we had to plug it into that formula, the square root of n, sorry, not n, p times 1 minus p over n, and that's what we would do for our standard deviation. So you're going to do those things each time, and then you're going to make sure that you type it into the calculator, normal CDF on all three of those, but you've got to make those adjustments for the standard deviation and the mean when they change for the samples. So go ahead and try those 5 problems, but again, keep in mind the similarities and the differences that we've learned in these past few sections.